Where are we all going? I mean, think about it for a second. You're on a rock right now. A wet rock, spinning in absolute darkness. And that rock is falling. Right now, you're falling through the universe at 630 kilometers per second, and you don't even feel it. We're running down an escalator that's moving up forever. We all just act like this is normal. The Earth goes around the sun goes around the galaxy is moving. You'll probably never think about it again. But stop and actually sit with it. You are never in the same place twice. Every second of your life, you're somewhere new in the cosmos. You have never been where you are right now. You will never be here again. And there's a reason for it. A specific direction, a specific place we're all falling toward. Back in the 1970s, some astronomers in Australia with a giant radio telescope started noticing something strange. After they accounted for everything, the Earth spinning, the Sun orbiting, the Milky Way drifting, there was still motion left over. A speed they couldn't explain. 630 kilometers per second. And not just us. Thousands of galaxies, all sliding toward the same invisible point in the sky. A point hidden behind the thick band of our own galaxy, in a blind spot called the zone of avoidance. They called it the Great Attractor. Something out there with the gravitational pull of tens of thousands of galaxies, dragging an entire region of the universe toward it. And here's the part that really breaks your brain. We will never get there. The universe is expanding too fast. The destination is receding faster than we can fall. And it turns out the Great Attractor isn't even the final answer. It's one step in something much, much bigger. If that got you curious, and you're the kind of person who can't stop asking where the hell we're all going, a quick like or subscribe keeps this channel alive. Now, let's get into it. The name Great Attractor came from necessity, not from triumph, not from a confirmed sighting, from the simple fact that astronomers could not see the source, could not map it, could not point a telescope at it and call it by any other name. They knew something was there. They knew it was pulling. So they named it for the only thing they were sure of, its pull. Here is what made this discovery unusual. The signal did not come from a single instrument, or a single team, or a single line of inquiry. It came from two completely separate directions at once. The first came from a survey of galaxies. In the 1970s, astronomers R. Brent Tully and J. Richard Fisher were using the Parkes Radio Telescope in New South Wales, Australia, to map the velocities of distant galaxies. This was painstaking work. Galaxy by galaxy, measurement by measurement, they were building a picture of how the local universe moves. And something in that picture did not fit. The galaxies were not drifting randomly. They were drifting together, not in all directions, in one direction. The second signal came from somewhere else entirely. Other teams, studying the cosmic microwave background, noticed that its temperature was not perfectly uniform. The CMB, the faint afterglow of the early universe, is the most pristine reference frame we have. It fills all of space. It should look the same in every direction, but it did not. One side of the sky ran slightly warmer. The opposite side ran slightly cooler. This is called the CMB dipole. Here is what scientists believed at the time. The dipole could be fully explained by motion. The Earth moves around the Sun moves within the Milky Way, and all of that local motion would produce exactly the kind of temperature imbalance they were seeing. They subtracted those known motions from the measurement, and a residue remained. Not a faint whisper, not measurement noise, a clean, directional signal. Hundreds of kilometers per second of unexplained drift, pointing toward a specific region of the sky. The two teams, working from completely different data, had arrived at the same conclusion. The Milky Way and thousands of its neighboring galaxies were being pulled coherently toward a single point, tens of millions of light years away. Not scattered, not random. Together, as if caught in a current. But here is where it gets strange. The destination was invisible. Not distant in a way that makes things hard to see, but hidden. The target lay directly behind the plane of our own galaxy, buried beneath the gas and dust of the Milky Way's central disk. Astronomers call this region the zone of avoidance. It is a band of sky where the density of interstellar material is so thick that optical light cannot pass through. Whatever lies beyond it, in that direction, is masked. Think about what that meant. 2 independent surveys had converged on the same spot. A real gravitational source was pulling our entire galactic neighborhood across the cosmos, and they could not see it. Not partly, not imperfectly, at all. So they gave it a name. The Great Attractor. Something massive. Something hidden. Something real enough to move galaxies across tens of millions of light years without announcing itself. Picture a raft on a dark ocean at midnight. No moon, no stars. The current is real. You can feel the pull, but you cannot see the shore drawing you toward it. You know it is there because you are moving. You know the direction because every other raft around you is moving the same way. The pull is not a theory. It is a measurement. The shore is inference, and the distance, hundreds of kilometers per second of residual drift sustained across tens of millions of light years, tells you the shore is enormous. That is the situation astronomers found themselves in. Pulled by something they could not observe directly, at a scale their instruments could register, but their eyes could not resolve. Now consider what this implies beyond the Great Attractor itself. The Earth moves around the Sun at roughly 30 kilometers per second. The Sun orbits the center of the Milky Way at around 220 kilometers per second. The Milky Way, together with its local group of galaxies, moves toward the Virgo cluster, and the entire ensemble moves toward the Great Attractor at hundreds of kilometers per second on top of all of that. Layer beneath layer. Motion within motion. Nothing in this picture is sitting still. Nothing is at rest. Not our planet, not our star, not our galaxy, not our local cluster. Everything is going somewhere. Everything has somewhere it is being carried. The Great Attractor is one name for one destination. But the destination is not fixed. It is embedded in a larger structure, and that structure is itself embedded in something larger still. The Milky Way is not falling toward a wall. It is falling through an architecture. That architecture had barely been glimpsed in the 1970s. Tully and Fisher had found the current. The CMB measurements had confirmed the residue. But what was generating the pull? What physical structure lay behind the zone of avoidance? What galaxy clusters and filaments and concentrations of mass could possibly be heavy enough to redirect thousands of galaxies across tens of millions of light years? None of that was known. What the 1970s gave us was the direction and the scale, the name and the mystery, not the answer. The biggest surprise was still ahead. To understand how we measure such motion, we have to start much earlier, before the CMB, before telescopes, before anyone had reason to suspect the ground itself was moving at all. For most of recorded history, the answer to that question seemed obvious. The Earth was still. Anyone could see it. Stand in a field on a clear night and watch the stars. They move. You do not. The sky rotates overhead in slow, stately arcs. The sun rises and sets. The moon tracks its arc. The planets wander across the fixed background of stars, tracing loops and reversals across the months. Everything up there moves. Everything down here holds steady. This was not ignorance. It was a reasonable inference from direct observation. And for a very long time, it produced predictions good enough to navigate by, plan harvest by, build calendars around. The mathematicians who worked on this model, in Mesopotamia and Greece and Egypt, and the Islamic world across centuries, knew their business. They could predict where Mars would be on a given night with real precision. The geocentric system worked. The problem was that making it work required a kind of mathematical ugliness. Planets don't move smoothly across the sky. They speed up. They slow down. They occasionally reverse direction entirely. To account for this, astronomers added circles within circles. A planet moved along a small circle, called an epicycle, whose center itself moved along a larger circle around the Earth. Then, epicycles on epicycles. The machinery grew elaborate. The predictions held. But the system was unwieldy in a way that nagged at certain minds. Then came 1543. On his deathbed, the Polish astronomer Nicholas Copernicus published a work called On the Revolutions of the Heavenly Spheres. He moved the sun to the center. He set the Earth in motion. In Copernicus's model, Earth was a planet, orbiting like the others, spinning daily on its axis. The heavens did not revolve around us. We revolved through the heavens. The reception was complicated. The Copernican model was not obviously simpler than what it replaced. It still required epicycles. It was not a clean mathematical victory, but it raised something the old model had never needed to answer. If the Earth is moving, why don't we feel it? This was not a small objection. It was a devastating one. If Earth hurtles through space in an orbit around the Sun, why is there no wind? If Earth spins on its axis once every 24 hours, why aren't we flung from its surface? The people who posed these questions were not foolish. They were pointing at a real problem in the physics, and for over a century, no one had a fully satisfying answer. The answer came with Newton. It came with the concept of inertia. A body in motion continues in motion unless something acts on it. We do not feel the Earth moving because we are moving with it. We share its velocity completely. There is no relative motion between us and the ground beneath our feet. We are not being dragged along behind it. We are part of it. And the vacuum of space provides nothing to push against. When you run through air, you feel the air. Take away the air. Take away all medium for resistance, and motion betrays itself in no sensation at all. That is why you can stand on a planet crossing 30 kilometers per second through space and feel nothing. Not a tremor, not a breeze, not a pull. The motion is real. The silence is also real. This was a profound shift, not just in astronomy, in how humans understood their relationship to the cosmos. The ground was not a fixed anchor point. It was a vehicle, and the vehicle was moving in ways that had no felt signature. But here is where it gets strange. Because Newton, having established that motion is real even when unfelt, still needed somewhere to measure it from. His laws of motion work beautifully, but they assume something. That there is a fixed universal reference frame somewhere out there, some absolute backdrop against which all motion can be properly measured. He never identified it. He assumed it existed. The mathematics required it. Albert Einstein, more than 2 centuries later, looked at that assumption and rejected it entirely. There is no fixed universal reference frame. There is no absolute backdrop. There is no universal ruler hanging in space against which all velocities can be checked. All inertial motion is relative. Think about what that means. 2 rocket ships drift through empty space. No engines running, no stars visible. One passes the other. Each pilot watches the other ship cross their field of view. Each pilot is equally justified in concluding that they are the one sitting still, and the other ship is the one moving. There is no measurement either pilot can perform, nothing internal to their ship, no reading on any instrument that will settle the question. From the physics, both views are correct. Both are valid descriptions of the same event. This is not a quirk. This is the foundation. From this single principle, Einstein built the entire framework of special relativity, time dilation, the speed of light limit, mass-energy equivalence. All of it flows from the recognition that inertial motion has no preferred reference frame. Now, there is a caveat worth understanding. Rotation is different. You can detect rotation without looking outside. Earth spins, and that spin leaves marks. The Coriolis force, the deflection that comes from rotating on a sphere, shapes hurricanes in the northern hemisphere to spiral counterclockwise, and typhoons in the southern hemisphere to spiral the opposite way. If every star in the sky were hidden, you could still deduce Earth's rotation from the behavior of large weather systems. Rotation is internally detectable, translation through space is not. So we arrive at the problem this entire story depends on. The Milky Way is moving. We established that in the previous century of observation. The CMB measurements confirmed it. The galaxy surveys confirmed it. Something is pulling us, and the pull is real enough to carry thousands of galaxies together in one direction. But if there is no universal reference frame, if translational motion through space cannot be felt or measured from inside alone, then how do we actually know how fast we are moving? How do we measure the Milky Way's velocity without a fixed ruler to measure it against? That question has an answer. It is not obvious. And it required finding something in the universe that could serve as a ruler, not an arbitrary one, but one built into the structure of the cosmos itself. What that ruler was, and how we learn to use it, is where this story goes next. The ruler was there the whole time. The universe is not static. It never was. Every galaxy in every direction is moving away from every other galaxy, carried outward by the expansion of space itself. That expansion does not have a center. It does not have an edge, but it does have something that turns out to be extraordinarily useful. It has a frame, not an arbitrary one, not one that any civilization chose or constructed. One that is woven into the fabric of the cosmos. Think about what that means. If the universe were perfectly still, there would be no preferred motion, no baseline, no way to say that any object was moving rather than at rest. Einstein was right about that. But the universe is not still. Space itself is stretching. And any galaxy that simply rides that stretching, neither gaining nor falling behind, can be said to be at rest relative to the cosmic flow. Any object that deviates from that flow has what cosmologists call a peculiar velocity. Not peculiar in the sense of strange, though what follows may feel that way. Peculiar in the technical sense, motion that is genuinely its own, motion that departs from the expansion. Peculiar velocities range from a few hundred to a few thousand kilometers per second. They are real motions through space, not carried by the expansion, but cutting across it. And with this tool, we can do something that would have seemed impossible to anyone working inside classical physics. We can describe, in absolute terms, how fast an object is moving through the cosmos. The expanding universe is the ruler. It was always there. We just needed to learn to read it. Now we can use it. And when we do, something remarkable happens. The motion you participate in every moment of your life turns out to be far stranger and far larger than it appears. Start with the simplest layer. The ground beneath you is moving. Earth rotates once every 24 hours, and how fast you are traveling because of that depends entirely on where you are standing. At the geographic poles, you are not rotating at all. You are simply spinning in place, marking time. At the equator, you are moving at roughly 1,600 kilometers per hour. At the mid-latitudes, where most of humanity lives, the speed is around 1,000 kilometers per hour. You carry all of that speed with you, invisibly, because everything around you shares it exactly. But it is real. Over an 80-year lifetime, rotation alone carries you approximately 1 billion kilometers through space. Not net displacement, not a straight line. A slow, unending spiral wrapped around a moving world. 1 billion kilometers just from the spin of the planet. The second layer is larger. Earth also orbits the Sun, and that orbit is not slow at all. The average speed is 30 kilometers per second. In a lifetime of 80 years, that orbit adds roughly 80 billion kilometers of travel. The orbit is nearly circular, so it does not produce a net displacement outward. You trace the same path again and again, but the distance covered is real, and 80 billion kilometers is not a small number. Set beside the rotational contribution, the orbital motion dominates almost completely. The spin is a whisper. The orbit is a steady, tireless drumbeat. But the orbit is not the outer edge of the layers. It is not even close. The Sun itself is moving. And here is where the numbers stop feeling like background data and start to carry consequences. The Sun orbits the center of the Milky Way at roughly 230 kilometers per second. One full revolution takes around 230 million years. The last time the Sun was in the same position in its orbit, the dominant life on Earth was early dinosaurs. The time before that, complex life had barely appeared. The Sun has completed fewer than 20 full orbits since it formed. That speed, 230 kilometers per second, is not just a measurement. It is evidence for something invisible. Think about what it takes to hold the Sun in that orbit. Orbital speed is not arbitrary. It is set by the gravitational pull of all the mass inside the orbit. If you know the speed, you can calculate how much mass must be present to produce it. When astronomers ran that calculation for the Milky Way, they found something they could not explain. The visible stars, the gas, the dust, all the matter that could be seen and counted and mapped, did not add up to nearly enough. Not by a small amount. Not by a rounding error. The visible mass of the Milky Way should have let the Sun drift free, flung outward billions of years ago. It was not flung free. It is still here, tracing the same orbit, steady and stable. Something invisible is providing the gravitational pull that keeps the Sun bound to the galaxy. Something with mass, enough mass to hold the entire solar system in a stable orbit for billions of years, but mass that does not emit light or absorb it or interact with ordinary matter in any way we can directly observe. We call it dark matter. And the Sun's own speed is among the clearest evidence that it exists. The ledger note stands, 30 kilometers per second was introduced as Earth's orbital speed in an earlier section. The Sun's galactic speed, 230 kilometers per second, appeared as a reference figure in section 1. Neither requires a fresh translation here, and none has been given. But the dark matter reveal is new, and it deserves the weight it carries. Beneath the orbit, there is a fourth layer, quieter than the others. The Sun does not travel in a perfect flat plane around the galaxy. It bobs. Slowly, over tens of millions of years, the Sun rises above the disk of the Milky Way, crosses through it, dips below it, and rises again. Like a buoy in a dark ocean, lifting on one slow swell and falling into the next, never stopping, never settling. The galactic disk is not a barrier. It is a density, a concentration of stars and gas and dust that the Sun passes through on each cycle. We are currently somewhere near the plane, moving gently through it, in the middle of a crossing that takes millions of years. The fifth layer is the one that is easiest to forget, because it is invisible in a different way. The solar system is not moving through average interstellar space. It is moving through a cavity, a region that is far emptier than the Milky Way's already extraordinarily thin average. The local bubble, as it is known, is a vast hollow in the galaxy, roughly 1,000 light-years across, carved out by the pressure of one or more supernova explosions millions of years ago. The density inside it is less than 1/10 of the Milky Way's average, and the Milky Way's average would already register as a near-perfect vacuum by any standard we could measure on Earth. The local bubble is emptier still. The solar system entered this cavity somewhere between 5 and 10 million years ago. It will take millions of years more to cross it. We are, at this moment, drifting through a bubble of almost nothing, blown into shape by a star that died before our ancestors walked upright. None of this motion is felt. None of it registers. You sit or stand or move through your day, carrying all 6 of these layers simultaneously, each nested inside the next, widening from a spinning planet to an orbiting world to a solar system tracing a slow galactic circle through a ghost of old fire. And still, none of it is the largest motion. The Milky Way itself is moving. Not just swept along by the pull of the Great Attractor, but moving towards something closer. Something it has been approaching for a very long time. That closest neighbor is Andromeda. Right now, if you stepped outside on a clear night and held your fist at arm's length against the sky, Andromeda would fill roughly that same span of darkness. It is already there, already enormous by any reasonable measure, already visible to the naked eye as a faint smear of light in the constellation bearing its name. We simply don't register it as large because it is dim. It is not a point of light. It is a galaxy, and it is enormous, and it is falling toward us. In about 2.5 billion years, Andromeda will no longer be a faint smear. It will dominate the entire night sky, a vast tilted disk of light stretching from horizon to horizon, its shape already twisted and distorted by tidal forces, its spiral arms pulled out of alignment by the same gravitational physics that raises Earth's ocean tides. The moon will be smaller and fainter by then. The familiar constellations will be gone, the stars that form them having drifted into new positions over billions of years. One object will hold the sky. And roughly a billion years after that, somewhere around 3.5 billion years from now, the galaxy filling that sky will blaze. Star formation triggered by the collision will surge to roughly 1,000 times its current rate. For a window of time that is brief by cosmic standards and almost incomprehensible by any other, the merging system will be crowded with newborn blue-white stars, blazing in enormous clusters. The sky above any surviving world, unlike anything the universe has produced in any era we have observed. The final merger comes billions of years later still, long after the sun has already died. But we are getting ahead of the story. To understand how we know any of this, we have to go back to Edwin Hubble in the 1920s. Astronomers at that time did not know that Andromeda was a separate galaxy. They thought it was a nebula, a cloud of gas and dust sitting somewhere within or just beyond our own stellar system. Hubble changed that. Using Cepheid variable stars, a class of pulsating stars whose brightness cycle reveals their true luminosity, he measured Andromeda's distance and arrived at a number that stunned the field. Andromeda sat 2.5 million light-years away. That was more than 10 times farther than any previously hypothesized boundary for the cosmos. The universe had just expanded by an order of magnitude. Andromeda was not a cloud within our galaxy. It was a galaxy in its own right, one of countless others scattered across a space far larger than anyone had imagined. That discovery raised an immediate question. Was Andromeda moving toward us? Measuring its velocity turned out to be harder than expected. When astronomers pointed optical telescopes at Andromeda and tried to measure the Doppler shift in its light, different parts of the galaxy gave wildly different readings. Some regions were moving toward us, some away, all depending on how that particular region of the galaxy happened to be rotating. There was no clean, single number. In 1957, Dutch astronomer Henrik C. van der Hulst found a way through. He used 21 centimeter radiation, a wavelength of radio light emitted naturally by neutral hydrogen atoms. Hydrogen fills galaxies in enormous quantities, and it radiates at this specific wavelength in a way that can be measured by radio telescopes, even when optical light gives only noise. Van der Hulst mapped Andromeda by radio and extracted a clean velocity. Andromeda was moving towards us at 296 kilometers per second. The uncertainty in that measurement was about 10 kilometers per second. The number was solid. Andromeda was clearly approaching. But here is where it gets strange. Knowing that Andromeda was moving toward us at 296 kilometers per second did not actually tell us whether it was going to collide with us. The reason is the difference between two kinds of motion. Radial motion is motion directly toward or away from us, and it is relatively easy to measure using Doppler shifts. Lateral motion is motion across our line of sight, sideways through space, and it is extremely difficult to measure because it produces almost no change in the color of the light we receive. Van der Hulst had measured the radial component precisely. The lateral component was essentially unknown, and a galaxy can be moving toward you at high speed, while simultaneously moving sideways fast enough to pass you entirely. Radial velocity alone could not confirm a collision. For decades, the collision remained a strong suspicion rather than a confirmed fact. In 2012, that changed. A team led by astronomer Sangmo Tony Sohn used the Hubble Space Telescope to measure the motions of thousands of individual stars inside Andromeda, tracking their positions across multiple years with extraordinary precision. This was not measuring the Doppler shift of light. This was measuring the actual movement of stars across the sky, tiny as that motion was. It took the full resolution of Hubble, years of patience, and careful subtraction of all other sources of apparent motion. When the team combined those lateral measurements with the known radial velocity, they had Andromeda's true three-dimensional velocity for the first time. The answer was unambiguous, not a glancing pass, not a near miss, a direct collision course. A collision is coming. What that collision looks like in practice is not what most people imagine. When two galaxies merge, the stars within them do not actually crash into each other. Stars are almost incomprehensibly small compared to the distances between them. Think of it this way. The space inside a galaxy is almost entirely empty. The stars are spread so thinly that two galaxies can pass through each other, the way two slow shoals of fish drift through each other in open water, each fish threading through the others without contact. The gas is different. Gas is spread across enormous regions and cannot simply thread through itself. When the gas clouds of two galaxies collide, they compress, tangle, and heat. They create shock fronts. They trigger exactly the star formation bursts described above. Stars themselves are not entirely unharmed by the merger. Close gravitational encounters between stars can alter orbits significantly. Some stars will be flung outward, ejected entirely from the merged system on long arcs into intergalactic space. Most will survive in new orbits, scattered and reshuffled, their old trajectories gone. Tidal forces, the same stretching effect that pulls Earth's oceans into bulges on opposite sides, will act across each entire galaxy during the interaction. The near side of each galaxy experiences a stronger gravitational pull from the other than the far side does. That difference stretches the galaxy. Spiral arms can be pulled away entirely, forming long filaments of stars and gas called tidal tails. Structures tens of thousands of light years long, trailing behind the interacting pair like streamers. Gas bridges can develop between the two systems, channels of material flowing back and forth as the merger proceeds. The first close interaction begins as early as 2 billion years from now. A single pass takes more than 100 million years. The two galaxies do not merge on a first encounter. They swing past each other, drawn back by gravity, pass through each other again, each cycle shorter than the last. The final merger, the point where the two systems fully combine into one, comes roughly 5 billion years from now, and what emerges is something very different from what went in. Isolated, the Milky Way would sip slowly through its gas reserves for well over 100 billion years. The merger burns through those reserves quickly. Each pass through Andromeda triggers fresh bursts of star formation, each burst consuming gas that will never be replenished. By the time the merged galaxy has fully settled, its supply of raw star-forming material is largely exhausted. New star formation slows, then stops. The galaxy, sometimes called Milkomeda by astronomers who study its projected fate, becomes a giant elliptical galaxy. Large, red, ovoid, no longer forming new stars, watching as existing stars age and fade one by one over hundreds of billions of years. We do not have to speculate about what this process looks like from the outside. We can observe it elsewhere in the universe, in other galaxy pairs already mid-merger. 290 million light-years away, a pair of galaxies called the Mice galaxies show exactly the tidal tail structure the models predict. Two galaxies just beginning their interaction, each trailing a long streamer of stars and gas behind them, the tidal forces already pulling their shapes apart as they move through their first encounter. 250 million light-years away sits ARP 220, observed by the James Webb Space Telescope in 2023. This is a merger already deep in progress. The collision triggered star formation so intense that the combined system shines at more than 100 times the brightness of the Milky Way. But that burst of formation has now ended. The gas is spent. What the James Webb Telescope captured was not the peak of the fireworks, but the afterglow. A merged galaxy already cooling, already quieting, already settling toward the dim red future that Milky will one day reach. One caveat the models carry honestly: the timing is not settled. The traditional timeline places the first interaction at roughly 2 billion years out, and the final merger at roughly 5 billion years. Recent simulations have suggested the merger might not reach completion until 8 billion years from now, or that it could be avoided almost entirely, depending on variables in the current velocity measurements that remain uncertain. We do not know the exact timing. What we know is the trajectory, and the trajectory is confirmed. Andromeda and the Milky Way are falling toward each other. The question is not whether the gravity between them is real. The question is how the details unfold across a timescale longer than the Sun has existed. And the Milky Way's motion toward Andromeda, substantial as it is not the largest pull on our galaxy. That pull comes from something much farther away, something the Milky Way has been falling toward far longer, and understanding it required learning to see the invisible. Understanding it required learning to see the invisible. And that turns out to be a problem with a surprisingly long history. In 1792, a French mathematician named Gaspard Monge was serving as Minister of the Marine in revolutionary France. The job was administrative. The problem he was working on was not. Monge wanted to know the most efficient way to move goods from one place to another. The shortest paths, the least wasted effort, given a specific distribution of starting points and destinations. He worked out the mathematics of optimal transport. At the time, it looked like a logistics problem, nothing more. Decades later, André-Marie Ampère extended Monge's equations. The mathematics grew more general. It described not just moving goods, but any situation where a distributed mass had to be rearranged from one configuration to another with minimum cost. Economists found it useful for modeling how resources flow between mines and factories. Then, the Second World War arrived, and a Soviet mathematician named Leonid Kantorovich applied the same framework to wartime logistics, to the practical problem of supplying a country under siege. The mathematics kept working. It did not care what was being transported. Here is where the story takes a turn that no one in 1792 could have anticipated. In the 1970s, a Canadian-American cosmologist named Jim Peebles was working at Princeton on a problem that seemed entirely unrelated. He was trying to understand how galaxies had assembled, how mass had moved through the early universe to collect into the structures we observe today. The problem was, at its core, a transport problem. Mass had started in one distribution and moved to another. And the equations that described that movement were Monge's equations, extended by Ampère, refined by Kantorovich. 2 centuries of logistics mathematics had, without knowing it, been describing the formation of galaxies. Peebles would win the 2019 Nobel Prize in Physics for his foundational work in physical cosmology. He was the son of a grain exchange worker and a homemaker. He had arrived at Princeton when the field of cosmology was considered something close to a dead end, a fringe pursuit with no rigorous future. He did not treat it that way. He treated it as a discipline waiting for the right tools, and he spent decades building them. French astronomer Roya Mohayyai and Russian astronomer Andrei Sobolevsky took Peebles' insight further. They turned what are now called the Monge-Ampère-Kantorovich equations into a working cosmological instrument. The logic of the technique is this: we know where galaxies are now. We know their velocities, at least partially, and we know how gravity works with high precision. Gravity is not mysterious, it follows rules. So if you know where something is and which way it is moving, and you know the force acting on it, you can run the clock backward. You can transport each galaxy through time, step by step, reversing its gravitational history, and reconstruct where it was billions of years ago. Not approximately, not metaphorically, mathematically. The limitation is honest and worth naming. Every step backward multiplies the uncertainty slightly. Small errors in current measurements grow as you push further back. The technique cannot reach all the way to the Big Bang. The earliest moments remain beyond its reach. but it can look back billions of years, and it can project forward just as precisely. Because the same equations that run backward also run forward. You are not guessing at the future. You are solving for it. Brent Tully, whose earlier surveys of galaxy velocities were the first thread we followed in this story, has spent years building on this foundation. His team's ongoing cosmic flows catalogs now contain tens of thousands of nearby galaxies, each one mapped not just as it appears today, but as it was billions of years ago, and as it will be billions of years from now. It is one of the most detailed reconstructions of cosmic motion ever assembled. The Great Attractor structure, its depth, its reach, its true gravitational weight, has become visible through that work in ways that direct observation alone could never achieve. But the Monge-Ampere-Kantorovich technique, powerful as it is, still depends on our measurements of galaxy velocities, and those measurements carry error. For every galaxy, there is uncertainty. Accumulate that uncertainty across tens of thousands of galaxies, and the picture, while detailed, is not perfectly sharp. The universe, it turns out, offers something better. Roughly 380,000 years after the Big Bang, something decisive happened. Before that moment, the universe was a hot, dense plasma, so energetic that electrons and protons could not bind together. Photons of light scattered constantly off the free electrons, trapped, unable to travel freely. The universe was opaque. Then, over roughly 10,000 years, the temperature dropped just enough for electrons to bind to protons and form neutral hydrogen. The plasma cleared. The photons that had been trapped scattered one final time and then traveled freely for the first time, in every direction at once, through all of space, simultaneously. That radiation is still traveling. We call it the cosmic microwave background. Every cubic centimeter of space participated in producing it. It fills the universe in every direction. It accounts for the vast majority of all the photons in the observable universe. And it is nearly perfectly uniform. Smooth to approximately 1 part in a million, an almost featureless glow of ancient light from a single moment 380,000 years into the universe's history. Think about what that means for measurement. We are surrounded in every direction by a wall of radiation that was emitted at essentially the same moment, at essentially the same temperature, from every point in space. It is a fixed reference, not a fixed reference in the Newtonian sense, not an absolute space, but something even more useful. It is a snapshot of the cosmological reference frame itself, the distribution of matter and energy at the moment the universe first became transparent, stamped into light and left for anyone who learns to read it. But here is where it gets strange. The cosmic microwave background is not perfectly uniform. It has a tiny asymmetry. One side of the sky is slightly hotter than the other, by exactly 0.0035 Kelvin toward the constellation Leo. The opposite direction, toward the constellation Aquarius, is cooler by exactly the same amount. This is called the dipole. A lopsided warmth, measurable, consistent, reproducible. There is only one explanation for it. We are moving. When you move through a bath of radiation, the photons ahead of you are compressed into shorter wavelengths, slightly hotter. The photons behind you are stretched into longer wavelengths, slightly cooler. The 0.0035 Kelvin asymmetry is a thermometer, and it tells us our speed relative to the CMB frame itself. The implied velocity is roughly 600 kilometers per second. Not relative to our galaxy, not relative to Andromeda, relative to the reference frame of the early universe. From that 600 kilometers per second, we subtract what we know. The Sun moves around the Milky Way's center. The Milky Way moves toward Andromeda. Strip both of those away, and something remains. A residual of approximately 300 kilometers per second, unaccounted for, pointing in a specific direction. That direction points directly at the Great Attractor, not nearby, not almost, directly at it. The CMB did not set out to confirm what the galaxy surveys suggested. It is a completely independent measurement, a different instrument, a different physics, a different method. and it arrived at the same answer. The galaxy velocity maps and the ancient light of the microwave background, built from entirely separate lines of evidence, drawn from entirely separate phenomena, converge on the same point in the sky. Something real is there. Something with mass enough to move an entire region of the universe for billions of years, at hundreds of kilometers per second, continuously. The question the mathematics and the microwave background have now made sharp is not whether the pull is real. That is settled. The question is what exactly is doing the pulling. What exactly is doing the pulling? That question demands an answer. But answering it directly, right now, would be like naming a city before you have drawn the map it sits inside. The Great Attractor is not a point floating in empty space. It occupies a position in a structure. That structure sits inside a larger structure, and that larger structure was not named, not fully recognized, until 2014. To understand what the Great Attractor is, we first have to understand the architecture it inhabits. The universe builds itself the same way, everywhere, always. It starts small. It grows through accumulation. The Milky Way began as a modest gathering of a few thousand stars in the dark, and over billions of years it pulled in smaller systems, absorbed dwarf galaxies, incorporated wandering clusters, until it became what it is today. That process was not unique to us. It is repeated trillions of times across the visible universe, each galaxy assembled through the same patient accumulation, each one the product of mergers too numerous to count. Astronomers call this hierarchical structure formation. The universe builds itself slowly, piece by piece, and each new piece is larger than the last. The first level of that hierarchy is the galaxy itself, already assembled, already complete. The Milky Way, Andromeda, every spiral and elliptical and irregular galaxy visible in any telescope, each one is the product of this process, already arrived at its current form. The second level is the group. Galaxies do not travel alone. They cluster together under mutual gravity into small collectives called groups, and our own neighborhood is one of these. We live in the local group, the Milky Way, Andromeda, a smaller spiral called Triangulum, and dozens of dwarf galaxies scattered around them. The local group is not finished. It is still in the process of collapse. We have already established in an earlier stretch of this journey that Andromeda is falling toward us at roughly 300 kilometers per second, and that the final merger lies billions of years ahead. But the story does not stop there. Roughly 100 billion years after the Milky Way and Andromeda complete their union, the rest of the local group, all of its remaining members, will fall inward as well and collapse together into a single enormous mega-galaxy, slow and dim and old. The third level is the cluster. Groups do not exist in isolation either. They move towards still larger centers of gravitational attraction, and those centers are clusters. A galaxy cluster is a collection of hundreds or thousands of galaxies, bound together by gravity, already assembled into a coherent whole. Clusters are the largest gravitationally bound structures in the universe that have already finished forming. Beyond them, at larger scales, things are still in motion, still assembling, not yet complete. The nearest cluster to us is the Virgo cluster. It already contains thousands of galaxies, and it is drawing tens of thousands more toward it. Our local group is among those falling in. We are moving toward Andromeda, yes, but simultaneously, we are falling toward Virgo. That infall began in the earliest moments after the Big Bang, when the slight gravitational advantage of the region that would become Virgo first began to draw matter toward it. It accelerated only a few billion years ago, as Virgo grew massive enough that its pull on the local group strengthened measurably. The fourth level is the supercluster, and here is where the story shifts. Clusters themselves move toward even larger groupings. These are superclusters, and because they are still assembling, their boundaries are loose, their definitions approximate, their edges contested. For most of the 20th century, astronomers struggled to define them precisely because spatial extent alone, simply measuring how far a grouping of galaxies reaches, does not tell you whether those galaxies are truly bound together or merely appearing close by coincidence. The first hints of something large in our corner of the universe came long before anyone knew what they were looking at. In 1863, William and John Herschel noticed an unusual excess of nebulae in the direction of the Virgo cluster. They did not know they were looking at galaxies. They did not know those galaxies formed a structure. They simply noted the excess and recorded it. Nearly a century passed before anyone understood what that excess meant. In the 1950s, Gérard de Vaucouleurs looked again at the distribution of galaxies near Virgo and recognized the shape of something coherent. He called it the local supergalaxy, later renamed the local supercluster. The Virgo cluster sat at its heart. It spanned roughly 100 galaxy groups and clusters and stretched more than 100 million light-years across. That was our home, as best as anyone understood it for decades. A vast assemblage with Virgo at its center and our local group somewhere near its edges, falling in. Here is where it gets strange. In 2014, Brent Tully, the same astronomer whose cosmic flow surveys had mapped galaxy motion across tens of thousands of galaxies, working with collaborators Hélène Courtois, Yehuda Hoffman, and Daniel Pomerida, proposed a fundamentally different way of defining what a supercluster is. Not spatial extent, not proximity, motion. They applied the Monge-Ampere-Kantorovich technique, the same mathematical framework we have already traced from Monge's 18th century transport problem through its modern cosmological application, and they used it to transform static maps of galaxy positions into dynamic pictures of galaxy flow. Instead of asking which galaxies are close to each other, they asked which galaxies are flowing toward the same gravitational center. The result was not a refinement of the old picture. It was a replacement. What astronomers had called the local supercluster, the Virgo supercluster, was not a single structure at all. It was one branch, one of four. The true structure was nearly 5 times larger in extent, containing roughly 100,000 galaxies spread across more than 500 million light-years, with 4 great branches reaching outward from a single gravitational focal point. Not a neighborhood, not a region, a continent of galaxies. Tully and his collaborators named it Laniakea, a Hawaiian word meaning immense heaven or open skies. They chose it deliberately, quietly. The word carries the weight of perspective. Immense heaven. That is what we live inside. The definition they established is built on motion, and it is worth following the logic of that definition precisely, because it redraws the map of where we are. The Milky Way belongs to the local group because we move toward a common center. Every member of the local group shares that inward drift, pulled by mutual gravity. The local group belongs to the Virgo branch of Laniakea because the local group, taken as a whole, moves toward Virgo. We are falling toward Virgo even as Andromeda falls toward us, and the Virgo branch, taken as a whole, belongs to Laniakea because it too is moving, flowing inward, toward the structure's gravitational center. Membership at every level is determined not by position, but by trajectory. Every one of the roughly 100,000 galaxies in Laniakea is heading in the same direction. All 4 branches converge. All that motion, across more than 500 million light-years of space, points inward toward a single destination. That destination is the Great Attractor. It sits at the beating heart of Laniakea, the gravitational focal point around which the entire vast structure is organized, toward which the Milky Way, the local group, the Virgo branch, and 3 other branches of tens of thousands of galaxies have been falling for billions of years. And still, the question hangs there, sharper now that the architecture surrounding it is clear. Something with mass enough to organize a structure 500 million light-years across cannot be a single object. What it actually is turns out to be far stranger than anyone expected. And what does the heart itself look like? That is the question the architecture finally allows us to ask. We have traced the 4 branches of Laniakea, watched them converge, mapped the flow of 100,000 galaxies toward a single gravitational center. The structure is clear. The destination is named, but the destination itself remains difficult to see. And the reason for that difficulty goes back to something introduced early in this story. The Great Attractor lies inside the zone of avoidance, that band of sky where our own galaxy's dust and gas pile up in such density that optical telescopes see almost nothing beyond it. The Milky Way's disk, viewed edge-on from our position within it, forms a curtain across a significant fraction of the sky, and the gravitational heart of Laniakea sits directly behind that curtain. For decades, this was the core frustration. We knew something was there. The galaxy velocity surveys said so. The CMB dipole said so. Two completely independent measurements, using different instruments and different physics, both pointed at the same hidden region. But pointing at a thing is not the same as seeing it. Then came a partial solution. Not a full one, a partial one. Certain wavelengths of light pierce dust that stops optical light entirely. Radio waves pass through. Infrared radiation, heat, passes through. X-rays pass through. Beginning in the 1970s and continuing through the 1980s and 1990s, astronomers turned instruments tuned to these wavelengths toward the zone of avoidance. What they received were glimpses, not a clear portrait, not the kind of image you can hold up and say, this is it, this is the thing. Glimpses through the veil. Partial views of a hidden landscape, like seeing shapes through frosted glass. But the glimpses were enough to find something. The best candidate, the object that fits the location and the mass requirements better than anything else, is a galaxy cluster called the Norma cluster, named not for any property of the cluster itself, but for the constellation we must look through to see it. The constellation Norma, a faint geometric shape in the southern sky, happens to lie along the line of sight between us and the cluster. So the cluster carries that name, borrowed from the sky it hides behind. And when you examine what Norma actually is, the scale of it is striking. A typical galaxy cluster is already enormous. Hundreds or thousands of galaxies, gravitationally bound, filling a region of space that can span tens of millions of light years. Norma is several times larger than that. Not slightly larger. Several times. It is one of the most massive accumulations of galaxies and hot gas in our local cosmic region. It sits roughly 220 million light years away. Think about what that distance means in travel terms. If you could move at more than 100 kilometers per second, a speed that would carry you from the Earth to the Moon in about an hour, the journey to Norma would still take more than 100 billion years. The current age of the universe is just under 14 billion years. So even moving at that speed, from the moment the universe began, you would not have crossed half the distance. You would not have crossed a fraction of it. Norma is not close. It is not something we are approaching in any meaningful human sense. And yet everything in our local region of the cosmos is approaching it. Not quickly. Not in any way that will matter on timescales humans can imagine. But gravitationally, structurally, Norma and the broader concentration of mass it represents sit at the bottom of an immense gravitational well. Imagine a landscape of gentle hills stretching hundreds of millions of light years in every direction, and at the center, a valley far deeper than any hill is tall. Everything rolls toward the valley, not because it is pushed, because the geometry of the space itself tilts that way. Norma sits at the base of that valley. It did not start there by chance exactly, but it did not build itself into that position by intention either. It began the way every galaxy cluster begins. Small accumulations of mass drawing together. Clusters merging with clusters. Gravity compounding on itself over billions of years. Each addition deepening the well slightly, drawing more material inward, deepening it further. But Norma happened to sit at a location in the early universe where the initial density fluctuations, the tiny ripples in matter distribution left over from the moments after the Big Bang, were just favorable enough to begin a cascade. That cascade has been running for billions of years. Norma continues to grow even now, collecting galaxies that are still falling inward, still crossing the distance that separates them from the center. But here is where the story requires a pause. Because despite everything the radio and infrared and X-ray surveys have told us, despite the clarity of the gravitational evidence and the convergence of independent measurements, our understanding of Norma itself remains incomplete. The veil has been partly lifted. Only partly. The dust of our own galaxy still blurs the picture. The measurements we have are real, and they are the best we can do with current instruments. But astronomers who study this region say the same thing consistently. Our portrait of the Norma cluster, of the Great Attractor's physical heart, is vague at best. Not settled, not fully resolved, partially seen. We know it is there. We know something of its size, its mass, its position. We have traced the flow of galaxies toward it from 500 million light-years away. We have watched the CMB dipole point at it from the beginning of the observable universe's transparency. And still, the thing itself is shrouded. There is something fitting about that. The Great Attractor, the name carried decades before anyone could say what it was, finally has a name to give in return. The Norma cluster, a region of sky, a collection of galaxies, a gravitational valley so deep that it organizes the motion of a structure more than 500 million light-years across. And we can see it only in fragments, only through instruments that translate invisible wavelengths into data we then interpret. The pull is real. The destination is named. The destination itself remains, in some fundamental sense, still just beyond what we can fully see. And the Norma cluster, it turns out, is not the end of the story. Because Laniakea itself is not the largest structure these surveys have uncovered. And yet, when the numbers are examined carefully, Norma is not enough. The mass is real. The gravitational well is real. The flow of galaxies toward it is real. But when researchers account for all of Norma's visible matter and fold in the dark matter surrounding it, the total gravitational pull still falls short. It cannot fully explain the velocity at which we and our neighbors are moving. The Great Attractor, it turns out, is not quite as great as it first appeared. Something larger lies beyond it, and Norma itself, vast and heavy as it is, appears to be in motion toward that something. This is the pattern the story has followed from the beginning. Each answer opens into a larger question. Each destination reveals itself as a waypoint. The scale widens again, and the previous layer, which felt like the end, turns out to be one more step in a longer journey outward. The something beyond Norma has a name. It is the Shapley supercluster. Harlow Shapley first glimpsed it in 1930 from the Harvard College Observatory. He could only dimly perceive what he was seeing. The instruments of that era were not equal to the distance. He recorded a concentration of nebulosity in a particular direction, a faint thickening of the sky, but he could not resolve its true nature or its scale. It was a detail at the edge of what the technology could register. We know now what he was looking at. The Shapley supercluster is our next nearest neighbor beyond Laniakea. It sits roughly 650 million light-years away. And it is, by every measure we can apply, larger than Laniakea itself. Its mass influences every galaxy, every group, every cluster around it for hundreds of millions of light-years in every direction. The Great Attractor does not simply pull us. It is itself being pulled toward Shapley's center. Think about what that means for the future. If the universe gave us enough time, Laniakea would eventually collapse inward, all its branches converging, all its mass drawing together into a single dense object, not unlike the Norma cluster at its heart. And then that object, that compressed remnant of Laniakea, would journey onward. It would fall toward a similar concentration of mass at Shapley's center. What Norma is to us, Shapley's core would be to a future Milky. The architecture repeats, one layer above the last. But the Shapley supercluster was not the only unexpected motion the surveys uncovered. There was something else. Something that did not fit the models, and whose reality is still debated. In 2008, NASA astronomer Alexander Kashlinsky identified what he called a dark flow. The method he used was subtle. When light from the cosmic microwave background passes through a galaxy cluster on its way to us, the moving cluster leaves a tiny imprint on that light, a faint signature of its velocity pressed into the photons as they travel through. This effect, known as the kinematic Sunyaev-Zeldovich effect, is one of the most delicate signals in all of observational cosmology. The imprint is smaller than small, but Kashlinsky compared these signals across the sky, cluster by cluster, and found something he had not expected. The clusters were not moving randomly. A large portion of them, spread across enormous distances, appeared to be flowing together, moving collectively toward a region of sky between the constellations Centaurus and Vela. The speed of this flow, between 600 and 1,000 kilometers per second, was faster than our own motion toward the Great Attractor. And the scale of it, if real, would involve a significant portion of the observable universe moving as one. Here is where it gets strange. The density variations in the universe, the slight clumpiness in matter distribution that drives all gravitational flow, are not large enough to explain a coherent motion on that scale. The known structure of the cosmos cannot account for it. Kashlinsky's interpretation was that something vast, perhaps beyond the observable universe, was exerting a pull we could not source to anything we can see. The claim attracted enormous attention. It also attracted serious skepticism. In 2013, the European Space Agency's Planck satellite, the most precise microwave background instrument ever built, searched for the same signal. It found no evidence of a dark flow. The debate was not resolved. It continues today. The dark flow remains what it was when Kashlinsky first described it. A possible signal. A disputed signal. A question the data has not settled. We do not know whether the dark flow is real. But separately, in the same years, a different kind of large-scale structure was coming into focus. One whose existence is not disputed. One whose origin reaches back to the very first moments of the universe. When the universe was a few 100,000 years old, it was over 1 million times smaller than it is today. All matter was compressed into a single hot, dense plasma. And through that plasma, sound waves moved, actual waves of pressure, crashing and reverberating through the primordial gas. These are called baryon acoustic oscillations. The name simply means sound wave patterns in ordinary matter. And they echoed through the early universe at enormous scales. Then, the universe expanded and cooled. The plasma transitioned to neutral gas, and when that happened, the sound waves froze. They stopped where they were. They left behind thin shells of slightly denser matter, rings of marginally higher concentration pressed into the fabric of the cosmos at the moment the music stopped. Over hundreds of millions of years, those shells accumulated more matter than their surroundings. More gravity draws more gas forms more stars gather into more galaxies. The frozen oscillations became the architecture for large-scale structure. Cosmologists today map them across enormous galaxy surveys, using them as a standard ruler to test models of cosmic history. In 2023, Brent Tully, together with Cullen Howlett and Daniel Pomereed, discovered that a set of known structures, the Sloan Great Wall, the CFA Great Wall, and the Hercules Complex, are not independent objects. They are arranged in a shell, a single curved surface more than 400 million light-years in radius, centered on the Boötes supercluster. Not a collection of separate structures, not a coincidental alignment. A single fossil echo from the primordial plasma, preserved across cosmic time and now mapped for the first time as a unified whole. They named it Ho'olelana. The name comes from the Hawaiian kumulipo, a creation chant that reaches back centuries. The line it draws from is this: Ho'olele kalana aka po uliuli. From deep darkness came murmurs of awakening. It is worth staying with that for a moment. The largest single structure yet identified in the observable universe carries the name of a sound rising out of darkness. And that is, in fact, what it is. A sound from the earliest universe, frozen at the moment matter and light finally separated. And now, visible as a shell of galaxies 400 million light-years across. The poetry is not imposed on the science, it rises from it. But even with Shapley's gravity, even with the possible pull of whatever lies beyond the observable horizon, the full motion of the Milky Way still could not be explained by gravity alone. The numbers still did not quite add up. Because motion, it turns out, is not only about being pulled towards something, it is also about being pushed away from something else. On the opposite side of the sky from the Shapley supercluster, there is not a mass. There is an absence, a void. It has been named the dipole repeller. We do not yet have an accurate picture of its shape or its full dimensions, but its effect is measurable. Voids are not passive empty spaces. They are filled with dark energy, the force driving the accelerating expansion of the universe, and that dark energy actively pushes the galaxies at the void's edges outward, away from the emptiness at its center. Not drawn toward a wall, pushed away from a gap. The Milky Way's motion is the sum of both. The Great Attractor pulls from one direction, the dipole repeller pushes from the other. Shapley pulls from deeper still. We are caught between forces we can measure but not escape, carried along a flow that has been building since the first moments after the Big Bang. And here is where the thread changes. Because it is the voids, driven by dark energy, that will ultimately prevent any journey toward the Great Attractor from ever completing. The pull is real, the motion is real, but the expansion of space driven by dark energy is also real, and it is accelerating. The gap between us and the Great Attractor is not closing as fast as the force pushing us apart is growing. The Norma cluster was not a destination we were approaching in any useful sense. It was a focal point we were always falling toward and would never reach. Dark energy is the reason why. And what dark energy does to the future of the universe and everything we have mapped inside it is where the story turns next. But before we follow dark energy to where it is taking us, we should go back to where it first appeared in our equations. Because the force now pulling the universe apart was not discovered in 1998. It was written into the mathematics decades earlier by the one person who should have trusted those mathematics most, and then deliberately removed. It was perhaps the only time in his career that Einstein did not trust his own equations. That fact alone deserves a pause. This was a man who had demonstrated in a single year a kind of sustained creative power almost without precedent. In 1905, he published the special theory of relativity, which dismantled the idea of a fixed universal reference frame and replaced it with a universe where time and space shift depending on how fast you are moving. In that same year, he identified a foundational principle of quantum mechanics, explaining why light interacts with matter in discrete packets rather than continuous waves. And in that same year, he published a paper that conclusively demonstrated the existence of atoms, settling a debate that had run through physics for more than a century. 1 year, 3 revolutions. So when Einstein turned his attention to applying general relativity to the universe as a whole, in 1917, the expectation was clear. He would write down the equations. The equations would tell him what the universe does, and he would accept what they told him. Here is what the equations told him. The universe does not sit still. It cannot. Gravity, operating across all the mass and energy distributed through space, produces a dynamic cosmos, one that is always in motion. The equations permitted 2 possibilities. The universe was expanding, or the universe was collapsing. What they did not permit was the third option, the one that almost everyone at the time assumed was true. A static universe, fixed and eternal, the same yesterday as it would be tomorrow. General relativity said that was impossible, and Einstein did not want to hear it. The reasons are not entirely clear even now. It may have been cultural habit. The static universe was the conventional picture, embedded deeply in how scientists of that era thought about the cosmos. Disrupting it required not just new mathematics, but a willingness to contradict a picture that had felt obvious for centuries. Whatever the reason, Einstein made a choice. He modified his own equations. He introduced a new term, a number he added to one side of the equation to balance it. The term had no measurable effect at the scale of the solar system, which is why it had never appeared before in any test of general relativity. But at cosmic scales, across the entire universe, it acted as a stabilizing force, counteracting the natural tendency of the equations to produce motion. A static universe became possible again. Einstein called this term the cosmological constant. It was a sleight of hand, a thumb placed quietly on the scale. And for a few years, it held. Then Edwin Hubble measured the sky. Using Cepheid variable stars as distance markers, Hubble established that the fuzzy patches of light scattered across the sky were not clouds of gas within our own galaxy. They were entire galaxies, each containing hundreds of billions of stars, each separated from us by distances so vast that light crossing them took millions of years. The universe was incomparably larger than anyone had thought. And then Hubble found something more. The galaxies were moving away, not randomly, not in all directions equally. They were receding, every one of them. The farther ones faster than the nearer ones, in exactly the pattern you would see if the universe were expanding. The cosmological constant had been introduced to prevent exactly this, and here was the universe, expanding anyway, as the equations had originally predicted. Einstein never made a public statement of regret, but his closest friends later recalled him describing the cosmological constant as his greatest blunder. He had added a term to preserve a static picture, and the universe had shown that picture to be wrong. The constant seemed to have served no purpose. It seemed, in the aftermath of Hubble's discovery, like something to be quietly discarded. But it was not discarded. Not quite. A constant you can add to an equation without breaking it, and then remove again without breaking it, has a strange kind of persistence. It never becomes incompatible with the mathematics. It simply becomes unnecessary, or so it seemed. And for decades, the cosmological constant drifted at the edge of cosmology, present in papers, present in debates, but treated as a relic of a mistake, rather than a genuine physical quantity. Then a Soviet astrophysicist named Yakov Zeldovich looked at it from a different angle. Zeldovich recognized something that changed how the constant had to be understood. In quantum physics, the vacuum of space is not empty in any simple sense. It is filled with energy. Particles continuously appear and vanish in it. Fields fluctuate through it. The vacuum has a baseline energy that is built into the structure of space-time itself. And Zeldovich saw that the cosmological constant and this vacuum energy were not two separate ideas. They were two mathematical expressions of the same underlying concept. Whatever Einstein had introduced as a stabilizing correction to his field equations, quantum physics had independently arrived at something that pointed to the same place. The constant, far from being a blunder to be forgotten, might be pointing at something real and physical about the nature of empty space. The question was whether that energy was actually there, whether it was doing anything. In 1998, two independent research teams were measuring the brightness of distant supernovae, trying to calculate how fast the cosmic expansion was slowing down. The assumption was that it must be slowing down. Gravity acts on all the matter in the universe, pulling it inward, decelerating the outward rush. The teams were measuring the rate of that deceleration. But the supernovae were not where they should have been if the expansion was decelerating. They were dimmer than expected, farther away than the deceleration model predicted. The expansion was not slowing down, it was speeding up, not flattening, not coasting, accelerating. The universe was expanding faster now than it had a billion years ago. And the most likely cause, the candidate that fit the mathematics without requiring anything exotic to be invented, was the vacuum energy of space-time, the energy that Zeldovich had equated to the cosmological constant, the term Einstein had introduced in 1917 and later wished away. Within weeks, cosmologists were reaching back for it. The greatest blunder had become the best available explanation for the strangest thing in the universe. A term added to preserve a static cosmos was now the leading candidate for the force actively tearing it apart. The little innocent correction, slipped quietly into the equations more than 80 years earlier, was the thing at the center of everything dark energy now means. And what it means for the future of everything we have journeyed through tonight is where the story turns next. And what it means begins with a structure we have already traced, galaxy by galaxy, branch by branch, across 500 million light years of assembled cosmic architecture. The local group, the Virgo cluster, and Laniakea itself were built the way all structures in the universe are built. Slowly, gravitationally, piece by piece, over billions of years of patient accumulation. The Milky Way falling toward Andromeda, the local group falling toward Virgo, the branches of Laniakea bending inward toward the Great Attractor. Each motion set in motion long ago, a trajectory older than the Earth, older than the Sun. In a universe governed only by ordinary expansion, those motions would have time to complete. The galaxies flowing toward the Great Attractor would eventually arrive. Laniakea would eventually pull itself close enough to hold together. The supercluster would finish forming. It would become not just a flowing structure, but a bound one. Home, in the deepest gravitational sense. But 5 billion years ago, something changed. Not gradually, not incrementally. A threshold was crossed. The universe had been expanding since the Big Bang, and as it expanded, the matter inside it grew thinner. Spread across larger and larger volumes, the average density of matter fell, and as it fell, a force that had always been present, woven into the fabric of space-time from the very beginning, finally had room to emerge. It had been sitting in the background through the age of radiation and through the long age of matter. Patient, latent, waiting, though not with intent. Waiting only because it was not yet strong enough to matter against everything else. 5 billion years ago, the density of matter dropped below the density of that force, and the balance tipped. That force is what we call dark energy. And here is what we know about it. We do not know what it is. We only know what it does. It causes the expansion of the universe to accelerate, not to continue, not to coast, to speed up, faster every year than the year before. But here is where it gets strange. Dark energy does not dilute the way matter does. As the universe expands and creates more space, matter spreads thinner across that space. Fewer atoms per cubic light year, less mass per volume. A diminishing gravitational claim on everything around it. But dark energy works the opposite way. More space means more vacuum, and more vacuum means more dark energy. The expansion creates the very force that drives more expansion. A feedback with no apparent ceiling and no signs of reversal. The best candidate for what dark energy actually is grows from quantum mechanics. Take a box, remove everything from it. Every atom, every photon, every particle you can measure or remove. The box is now as empty as physics allows, and yet it is not empty in the way intuition suggests. Quantum mechanics tells us that the vacuum itself is alive. It is a roiling, bubbling sea of fundamental particles constantly popping into existence and vanishing again, borrowing energy from nothing and returning it in fractions of a second too small to observe. The vacuum has its own intrinsic energy. It is the baseline energy of empty space, even space containing nothing at all. Dark energy appears to be a manifestation of that vacuum energy. And because it is intrinsic to space itself, every new volume of space that the expansion creates carries that energy with it. More empty space, more vacuum, more dark energy. The process does not slow. The process compounds. At present, dark energy makes up roughly 70% of everything the universe contains. Matter, all of it combined, visible and dark, accounts for most of the rest. 70% is already a commanding lead. But the trajectory does not hold there. As expansion continues, matter thins further. Dark energy grows. The share becomes 80%, then 90, then 99, and then more, building on itself toward a universe that is almost entirely the energy of empty space, accelerating away from itself at a rate that climbs without apparent end. The voids are where you see this most clearly. We have already traveled through the voids in this story. We have seen them as the spaces between filaments, the absences around which the cosmic web is built. They seemed passive, the residue of structure rather than the engine of anything. That picture is not complete. Voids are almost entirely empty. The occasional thin filament of ionized gas threads through them. A dwarf galaxy wanders their interiors now and then. But for the most part, voids are nearly pure vacuum, which means they are nearly pure dark energy. And dark energy repels. It drives the expansion of space. And so the voids, those vast stretches of near nothing, are the precise locations in the universe where accelerated expansion is happening fastest. The voids are not passive. They are the engines. As time passes, voids grow. They push against the filaments and walls at their edges, driving the galaxies there apart faster than gravity can pull them back together. Adjacent voids merge, becoming larger voids with more vacuum, more dark energy, more repulsion. The cosmic web does not hold. The filaments thin. The walls fragment. The galaxies at the boundaries are driven apart by the growing emptiness between them, carried outward on the accelerating expansion that the voids themselves are fueling. The cosmic web is being unmade by its own absences. What survives this unmaking and what does not comes down to a single question. Is the structure already gravitationally bound? Already pulled close enough that local gravity can hold against the expanding space around it? The local group will survive. The Milky Way, Andromeda, Triangulum, and the dozens of dwarf galaxies already drawn into the group's shared gravitational embrace are close enough, and the local gravity strong enough that the accelerating expansion cannot pry them apart. They will continue their mergers. Milkomeda will form. The remaining members will fall inward over the billions of years that follow. The local group will complete itself as a single mega-galaxy, sealed against the larger unraveling by the gravity it already possesses. The Virgo cluster will survive. The thousands of galaxies already locked into Virgo's deep gravitational well will remain there. Clusters are the largest gravitationally bound structures that have had time to fully assemble. They will persist as isolated harbors, sealed islands in an expanding ocean, each increasingly alone as the galaxies beyond their gravitational reach are carried away. Superclusters will not survive, not Shapley, not the millions of others woven through the observable universe, and not Laniakea. This is the reveal that the story has been building toward, and it lands quietly. Laniakea will never finish forming. The galaxies flowing along its four great branches toward the Great Attractor will not complete that journey. The supercluster, 500 million light-years across and carrying 100,000 galaxies in slow gravitational drift toward a common center, missed its window. Dark energy's turnover happened 5 billion years ago. Laniakea had not yet pulled itself close enough. The accelerating expansion began before the supercluster could bind itself against it. And now it cannot. The branches will slow. The inward motion will stall. And then, over timescales longer than anything in human experience can anchor, the branches will begin to drift apart. Not violently, not suddenly, but irreversibly. The immense heaven will disperse. The open skies of Laniakea will grow more open still, until the structure that bears that name is no longer a structure in any meaningful sense. Only a memory written in the motions of galaxies that are no longer flowing toward anything. This is what the cosmological constant does when it returns from banishment, not as a stabilizer, not as the quiet correction Einstein inserted to preserve the cosmos he expected, but as the force that determines which structures in the universe have a future and which do not. The little innocent term slipped into the equations in 1917, proved in 1998 to be real, and it is doing its work right now on Laniakea, on the cosmic web, on everything we have spent this journey learning to see. And the question it leaves behind is not whether this unmaking can be stopped. It cannot. The question is what it means that we can see it happening at all. That question is the one this entire journey has been building toward. What does it mean that we can see it happening at all? What does it mean that we are here, in this brief window of cosmic time, watching structures dissolve that no future observer will ever see intact? Let's follow our own journey to its end. The Milky Way and Andromeda will still merge. That much is settled. Billions of years from now, the collision will unfold, the star formation will blaze, and Milky will take shape from the wreckage of two spirals. The rest of the local group will eventually follow, falling inward over 100 billion years or so, until a single mega-galaxy remains. One object. One deep, gravitational well. The heir to everything the local group ever was. But it will never reach Virgo. It will never reach the Norma cluster. It will never close the distance to the Great Attractor, not even the distance to the nearest galaxy outside our gravitational embrace. The fall that has been underway since the earliest moments after the Big Bang, the motion that pulled this whole story together, will not complete. Dark energy will see to that. Here is where it gets strange. The journey toward the Great Attractor does not simply stop. It reverses. Billions of years from now, as expansion accelerates and the gulf between us and the Norma cluster grows faster than gravity can close it, our motion in that direction will slow. It will stall. And then, the distance will begin to open, not because we turned away, but because space between us and everything beyond our gravitational reach is stretching at a rate nothing can match. The Great Attractor will recede. The Shapley supercluster will recede. Every cluster and filament and wall beyond the local group will recede, growing dimmer as the light they send toward us gets stretched thinner and redder. Over hundreds of billions of years, they will reach a horizon, not a physical wall, a boundary defined by expansion itself, beyond which no signal can ever reach us because the space between us and its source is growing faster than light can cross it. One by one, they will slip past that horizon and go dark, not destroyed, not gone in any physical sense, simply unreachable, simply invisible, simply no longer part of our observable universe. And then, the mega-galaxy will be alone. Not alone the way a remote island is alone, surrounded by open water but still under the same sky as everything else. Alone in a way that has no good comparison in human experience. Adrift in a sea of nothingness, with every other galaxy slipped beyond the horizon, with nothing in any direction but the expanding void. Trillions of years from now, the mega-galaxy that was the local group will be the only structure left in its observable universe. The only light, the only gravity, the only motion that still has anything to measure itself against. But even then, motion does not stop. Inside the mega-galaxy, stars are still moving. Gravitational interactions between them are still happening. Billions of encounters accumulating over timescales that make the current age of the universe seem like a breath held briefly and released. And those encounters have a consequence. Occasionally, a close gravitational interaction between two stars will transfer energy from one to the other. The receiving star accelerates. If it accelerates enough, it reaches escape velocity. It slips out of the galaxy's gravitational embrace and crosses into open space. Wait, that is what space will be at that point. Not open in the sense we use the word now, meaning vast and empty but still structured. Still webbed with filaments, still oriented toward attractors and clusters and walls. Open in the sense of having nothing in it at all. And once a star crosses into that space, it will be caught by the same accelerating expansion that took the distant galaxies, flung outward, separated from the mega-galaxy by distances that grow faster than light, never to return. One by one, star by star, the galaxy diminishes. This is not a sudden catastrophe. It is a long, slow draining. Each ejected star takes with it a small fraction of the galaxy's mass, a small piece of its gravitational coherence. The process unfolds over timescales so vast they resist any comparison. But it continues. And it does not reverse. The same gravity that built galaxies, merged them, drew the local group into one structure, eventually scatters the remnants of that structure into permanent isolation. The same fate applies to everybody, on every scale. dead stellar remnants drifting through the megagalaxy until a gravitational encounter sends them wide. Frozen planetary husks orbiting cold cores until those orbits decay or a passing perturbation breaks them free. Hundreds of trillions of years from now, every macroscopic object, every remnant of every star that ever burned in the local group is separated from every other by a gulf of expanding space that nothing can cross. Not isolated in the way the mega-galaxy was isolated, still whole, still lit from within. Isolated individually, each object utterly alone. The space between them is not simply large, it is growing, and growing faster than light can cross it. This is not motion through space in the ordinary sense. Space itself is expanding, the fabric stretching between objects that are not themselves moving toward or away from each other. There is no speed limit being broken. There is simply more space, continuously, everywhere at once, separating things that have no way to reach each other even at the maximum speed the universe allows. With that comes something quieter than any event this story has described. Something that is not a bang, not a collision, not a transition with a date or a discoverable moment. With nothing outside each isolated remnant, there are no other stars to gauge motion against. No Hubble flow to compare to. No other sources of attraction or repulsion orienting anything toward anything else. The only companion is the cosmic microwave background. That ancient bath of dim photons released nearly 14 billion years ago, when the universe first turned transparent, stretched so thin by then that it barely whispers. But even that will fade as expansion redshifts it toward wavelengths too long to interact with anything. And this is where the journey ends. Not in destruction, not in darkness exactly, though darkness is what remains. In something more fundamental. Motion was always defined relative to something else. The Earth moves relative to the Sun. The Sun moves relative to the Milky Way. The local group moves relative to the CMB, relative to the Great Attractor, relative to the structures we have spent this whole story learning to see. Every measurement of velocity requires two things: the object moving and something else to measure it against. When the something else is gone, motion becomes meaningless, not impossible, not forbidden by any law, meaningless. There is no frame of reference in which one result differs from another. The concept dissolves, not because anything stops, but because the word stop no longer refers to anything real. The universe, what remains of it, finally comes to rest. Not because it chose to, because rest and motion, at that point, are the same.